The first pictures from Rubin are finally here. Construction begins on the LISA mission. Webb directly images a Saturn-sized exoplanet. And do pulsars have mountains? And in Space Bites Plus, a fast radio burst is coming from inside the solar system. All this and more in this week's Space Bites. Well, we've all been waiting for it, and we are finally here. We've seen the first images from the Vera Rubin Observatory. And so we knew the images were going to be coming out, and they had an embargo that was going to be lifted on Sunday evening at 9 o'clock my time, midnight Eastern time. And so dutifully at 9 o'clock, I checked out the web page, and I had not seen them. Even though it was an embargo and space journalists got a chance to see them early, I don't like embargoes, so I just waited until they were publicly available. And I was able to see the pictures and be blown away by them, like I'm sure all of you were. And then Monday morning, we got a press conference from the people working with Vera Rubin, sort of explaining some of the other details, all the people who worked on it. And we got some additional videos and information. So what we saw was really kind of two big images and then one really cool piece of information about asteroids. So with the images, we saw this incredible image of the Trifid Nebula, Lagoon Nebula complex. And these are two star-forming regions that are very close to each other. They're really famous. They're located near the center of the galaxy. I've taken pictures of them with a small telescope, but nothing like this. And so this picture was made of 678 separate exposures that were then taken for about 30 seconds and then stacked up together to create this just incredibly detailed image of the complex. And then the other image that they released was of the Virgo cluster. And this is the sort of largest cluster of galaxies close to the Milky Way. And they kept showing how you don't own a screen big enough to be able to see all of the detail in this picture. And that's because it was taken with Vera Rubin's 3.2 gigapixel camera. You would need many, many screens bolted together to be able to see the full image at the full resolution. But they were able to provide a viewer on their website. So you can go and zoom in to different parts and zoom back out and move to a different spot and zoom in to really get a sense of the level of detail that are in these images. And again, this was made with hundreds of separate exposures and then stacked up. But this is a demonstration of the field of view that you're going to get with Vera Rubin. The galaxy picture was made of sort of like two separate Rubin fields of view, but it's going to be taking these images about every 30 seconds. 30-second exposure, move to the next target, 30-second exposure, move to the next target. Like a lot of people were really oohing and aahing over how pretty these images are, and they're great. But I mean, we've all seen really pretty nebula pictures, really cool pictures of galaxies from Webb, from Hubble, from the European Southern Observatory. That's not what is amazing about Vera Rubin. What's amazing is its ability to move quickly and watch as things are changing. It is video compared to images, where they really demonstrated the capability and the true purpose of Vera Rubin was looking for asteroids. They examined a small spot in the sky. They looked for 10 hours of observations, and they turned up more than 2,000 previously undiscovered asteroids. And to give you context here, every year astronomers add about 20,000 asteroids to their database of asteroids. And in 10 hours, Vera Rubin found over 2,000. And so when it is fully operational, it is going to be finding so many asteroids, it's kind of ridiculous. In total, astronomers have been scanning the sky. They found asteroids for well over 100 years. They know of about 1 million asteroids in the solar system. Vera Rubin will find an additional 4 million in its next 10 years of operation. The telescope is going to be taking these relatively short exposures using this incredible, powerful camera. It's going to move to the next spot, take another one, move to the next spot. And over the course of about 3 nights, it will have surveyed the entire sky that it can see from the southern hemisphere. Then it's going to start again and just do another version of this. And then it's going to do it again. It's going to do it again. And over the course of the year, of course, the sky will change. And over the course of its 10-year main operations, it's going to see every part of the sky about 800 times. And then astronomers can do a couple of things with this. One is that they can get like a single stacked data image of this one spot in the sky, where you've added these 800 exposures together to make one really detailed image. But also you can check how things have changed over time, because you will have supernovae going off, asteroids passing through between different images that were taken. And so imagine that you could just think about any part in the sky, and then you could roll the video forward and backward to any spot in time and then see what the sky looked like at that moment. And so if someone is noticing that a star is no longer there in one galaxy, they can go back through the Vera Rubin data and find the moment when that star disappeared. And then what was there before the star? It's this time element is what makes this observatory so special. And that I can imagine that you're going to eventually be able to just like make these animated sequences of 800 frames of one spot in the sky and watch as asteroids are zipping through and supernovae are going off and variable stars are pulsing, getting brighter and dimmer over time, and novae are going off. All of this stuff that's happening dynamically. And the thing that I'm most excited about is the things that the universe was doing when we weren't looking. Like, we know that there are supernovae, we know there are asteroids, but there's stuff that we don't know. We will find them. We will see them, and then we will understand more about the cosmos. In just its shorter exposures, Vera Rubin will be able to see objects down to 24.7 magnitude, which is very dim. That is a very good telescope. But in the longer stacked images, it'll be able to see objects as faint as 27.5, which is really respectable. Now, compare this to the Hubble Space Telescope, which is able to see images as faint as 31.5 magnitude, but it's looking through a tiny straw and it's out in space. Vera Rubin is just looking at this enormous swath of the sky and then moving on. So it is quite a telescope. Now, this is just the beginning of the story. We've had this first light. They're still in this commissioning phase. They're not going to do the full operation and begin until later on this year. But when they do, there's going to be this incredible data pipeline. Tons of information is going to be coming out. We're going to discover these supernovae in pretty much real time. We'll know of so many asteroids. It's going to be a crazy time for science. I think for a lot of news reporters out there, this is when the story ends, right? Oh, a new telescope. There's pretty pictures. Moving on. This is where my work begins, because I'm going to be reporting on all of the incredible discoveries that are happening over time over this next decade. If you want more information about Vera Rubin, I did a very long interview with the director of the observatory, Dr. Edward Ajar, and so we'll put a link in the show notes so you can check that out and give a better sense of what this observatory is going to do. But as you could probably tell, I'm pretty excited and I can't wait to see what happens next. And if you want to play with the data from the images, you can do this yourself. There's a link that they put in their press release, and we'll put a link to that. And we've got a story about this from Mark Thompson on Universe Today. We've only been detecting gravitational waves for about a decade, and this is with ground-based telescopes. You've got LIGO, you've got Virgo, and you've got the Kagra observatories. And these are limited by the kinds of gravitational wave events that they can detect. Sort of stellar mass black holes crashing into each other, black holes crashing into neutron stars, maybe neutron stars crashing into neutron stars crashing into white dwarfs. That's about it. But there are a lot of other gravitational wave events that are out there. They are just beyond the detection capabilities of these ground-based observatories. And then the other way that astronomers detect gravitational waves is using pulsars. And so the pulsar timing array has confirmed the existence of this kind of background sloshing of gravitational waves across the universe coming from merging supermassive black holes, but not any specific events. They can't pin them down to where they're happening. To truly detect, say, colliding supermassive black holes, you've got to go to space. And this is something that the European Space Agency has been planning now for a long time with their Laser Interferometer Space Antenna, or LISA. And the LISA mission is going to be 3 spacecraft that are flying information at a distance of 2.5 million kilometers. They're going to be firing this laser back and forth in between the different spacecraft. And so as a gravitational wave passes them, then the spacecraft will be pulled a little farther apart or pushed back together, and they'll be able to detect when that change in the length of these laser arms are happening. And then from that, they will be able to detect potentially these giant supermassive black hole mergers and other events that are outside the capabilities of the ground-based observatories. And like I said, ESA's been working on this idea for a long time. They launched a Pathfinder mission of one of these satellites to prove that the technology was going to work, that it was going to have the level of accuracy that was required. They learned all their lessons. Then they planned the full version. And last week, they finally signed a contract to begin the construction of the full LISA mission. The company they chose is out of Germany called OHB System AG, and that's the prime contractor. But there's going to be a lot of other subcontractors working with this. And so if all goes well, LISA will launch in 2035, and hopefully after that, we will detect merging supermassive black holes and other extreme events for the first time. And we've got a story on Universe Today about this from Andy Thomaswick. The James Webb Space Telescope has a lot of jobs. Of course, it is looking out to the edge of the observable universe. It is looking at newly forming planetary systems, and it has also been used to observe the atmospheres of exoplanets as they've been passing in front of their host star. But now, Webb has found a planet of its own. The planet is located in the TWA7 system. And this is a newly forming kind of protoplanetary system. You've got a red dwarf star at the center, and then there are these protoplanetary rings in this disk around this young star. And astronomers are using Webb to observe the disk, and they detected the presence of a planet in one of the gaps of this disk. And based on their calculations, this planet is about the mass of Saturn. It's about 50 astronomical units away from its star, and they were able to measure the temperature at about 50 degrees Celsius. And when you look at this image, you can see where the star would be, but it's blocked out because Webb is using its coronagraph, which is a way to block the starlight to reveal the fainter objects that are orbiting around it. And so this is the lightest, smallest exoplanet that has been directly observed so far. What I like about this is that it is a sort of preview of what we're going to get with the Roman Space Telescope when it launches in 2027. It's got a better version of a coronagraph. It's designed to be able to do these direct imaging of exoplanets around sun-like stars. And so it should be able to detect Jupiter-like planets around sun-like stars. Now we've got a story about this exoplanet from Andy Thomaswick on Universe Today. But this discovery was perfectly timed to a paper that I found on Archive just a couple of days ago, where astronomers were calculating how well Webb could be used to directly observe exoplanets in the Saturn to Jupiter size range. And they calculated that if you pointed Webb at stars that are within about, say, 60 light years of us, it should be capable of detecting Saturns and Jupiters around sun-like stars at roughly the distance and age of our own solar system, and not a young star, not a red dwarf star, like a proper main sequence star. And in fact, two instruments on board James Webb should be able to make this observation. It's got MIRI, it's got the NIRCam, although MIRI is better for this kind of an observation. And so the researchers simulated, if there were planets around these stars, what kinds of observations, what should be within the reach of James Webb. The way this science works is that now we have had a couple of years where astronomers are working with Webb, they're understanding the capabilities, and then they're starting to simulate what kinds of observations should be possible. And then the next step is that they get time on the telescope to try and make those observations a reality, and then learn and then keep iterating. And so, again, even though we're still 3 years in using James Webb, the best observations are yet to come because astronomers are still learning how to work with both the telescope and the data that it produces. We've got a story about that by Evan Goff. Yeah, it's just exoplanet day. So I got one more interesting exoplanet story. Now, hot Jupiters, these are planets that are like roughly the size of Jupiter or larger, and they are orbiting extremely close to their star. And actually the first planet ever discovered around a sun-like star was a hot Jupiter. Now we know of thousands and thousands of exoplanets, and these are rare. They're easy to see because they have such an extreme effect on their star, but they're actually not very common. About 1% of stars have these hot Jupiters. There's an even more rare version of this, which is binary hot Jupiters. So you have two stars in a binary system, and both stars have a hot Jupiter. And how do you get this? Well, astronomers did some simulations and they calculated that in fact, if you have binary stars, they can force planets in the other system into a hot Jupiter arrangement. You get this kind of mirroring between the two stars in the binary system, where both have a hot Jupiter. The gravitational interactions between the stars and their planets and their partners push these planets closer and closer to become these hot Jupiters on both sides. We've got a story about that by Matt Williams. Every week we do a vote on our channel where you tell us what you thought was the best news story of the week. And the winner last week was that the Vera Rubin images are coming soon. I wonder what the winner's gonna be this week. Anyway, while you're watching this video, we have put the vote into the post tab on our channel. So go there and check it out. But, click on a bunch of the polls and then that will remind YouTube that you like to interact with this kind of content. Of course, the best chance, subscribe to our channel, click on the notifications bell, and then just obey the algorithm. Pulsars are neutron stars. So you get a star with, say, 8 to 20 times the mass of the sun. It lives a relatively short life, explodes as a supernova. You're left with a degenerate remnant, a neutron star. The neutron star has several times the mass of the sun compressed down into a region that is the size of a city. They're about 10 kilometers across. And yet they have all of these neutrons and electrons that have been smashed together into neutrons. It's like one great big atom. And when they first form, they're often spinning very rapidly and they're putting out these pulses of radiation. And those are pulsars. So all pulsars are neutron stars, and they can also be magnetars. But anyway, as a pulsar ages, its spin rate slows down. It's essentially leaking radiation through gravitational waves, and that spin rate slows down, and eventually the radio beams shut off. And there is this point where it happens called the death zone for pulsars. But astronomers have found pulsars that are spinning more slowly than the theories predict should be happening. How can they continue to be producing these radio waves beyond this minimum point? And so a team of astronomers are suggesting that in fact it's surface features on the pulsar that is allowing it to continue to produce radiation. They think that there are mountains on the surface of pulsars. Now, you have to use the term mountain very carefully, because these could be features that are maybe 1 centimeter tall. But on a pulsar, where everything's so compressed and the gravity is so extreme, 1 centimeter, that's a mountain. And so then these mountains would amplify the local electric field and would allow the pulsar to accelerate particles and create radio waves long after it should have been prevented. But what's also interesting about this is that, now you have these sort of slight instabilities on the surface of the pulsars, and they're rotating very rapidly. And you could use this as a way to try and probe the interior of the pulsars. Maybe it's not just one smooth collection of neutrons. Maybe it has layers, and maybe there's even strange forms of matter inside the pulsar that you could use these instabilities to measure. We've got a story about that by Mark Thompson on Universe Today. It's a good week for first light. So in addition to the first light that we saw from Vera Rubin, we've got first light from another new space telescope called the Coronal Diagnostic Experiment, or CODEX. And this is a new instrument that was installed on the outside of the International Space Station. It was launched as part of a cargo delivery late last year, and then it was installed on the exterior of the station by astronauts. And so what you're looking at in this picture is a view to the sun. And again, back to this term, a coronagraph. It is blocking the light from the sun, revealing the faint corona that surrounds the sun. Very similar to what happened with the Proba 3 satellite that we talked about last week. And this corona, this is the place where the solar wind begins. And so CODEX is able to see sort of faint filaments and changes in this outer atmosphere that will then be able to be matched up with the images being seen from Proba, the observations made from the Parker Solar Probe, the Daniel Cain Solar Telescope, the Solar Orbiter. Like, there's a lot of instruments all coming together, observing the sun and helping us get a better sense of space weather. And of course, this is really important because sort of the future of technology on Earth depends on us understanding space weather. We've got a story about that by David Dickinson on Universe Today. Now, if you remember way back to early June, iSpace's Hakuto-R Mission 2 was going to be doing a landing. It was going to make up for the failed landing that had happened with Mission 1. And so we watched with bated breath as the lander got closer and closer to the surface of the moon, and then the communications got cut off. And as it got cut off, you could see that it wasn't going the right speed for a soft landing. And so it was assumed it was a goner. And then a few hours later, the folks from iSpace said that they had lost connection with the lander. They were going to try to restore it, but they were going to begin investigating. And so this week we got an announcement from iSpace where they think that the problem came from the laser rangefinder. And this seems to be a problem that's cropping up quite a bit. I don't know, some kind of laser rangefinder conspiracy. And the laser rangefinder was working fine when they installed it in the spacecraft and they had tested it. And so they think that maybe some kind of degradation of the instrument had happened because it was in space for quite a while before it actually made its landing attempt. But iSpace just doesn't give up. So they said in the press release about sort of the problem analysis that they are still planning their mission 3 and their mission 4 right on schedule. So hopefully they'll get this right eventually. I really like their determination to land safely on the moon. Now I've got a story about that by Matt Williams. Now the space news that we're talking about here in Space Bites is just a fraction of all of the space news that we're covering over at Universe Today. And the way you can get the full understanding is to read my weekly email newsletter, which I send out every Friday. For example, a mission to collect a sample from asteroid Apophis as it's flying by. We got a story by Andy Thomaswick. Why Antarctica is the perfect place to study snowball Earth, that there are these little melt ponds in Antarctica, which has not only bacteria, but actually larger multicellular organisms. And maybe that's how life survived snowball Earth hundreds of millions of years ago. We've got a story about that by Mark Thompson. And then camera systems as scientific instruments in the Artemis 3 EVAs. And so when the astronauts return to the moon as part of Artemis 3, they're going to be bringing state-of-the-art full frame camera system with them. They're going to be able to do live streaming. They're going to be able to take just incredible images, and they will be using them for a lot of science. We've got a story about that by Lawrence Tugnetti on Universe Today. Now, I send out my weekly email newsletter on Fridays. It goes out to 70,000 of my closest friends. It's completely free. I write every single word in it. And so you can go and sign up. Go to universetoday.com/newsletter. Now, we have a longer version of this video with one extra story over on Patreon. We call it Space Bites Plus. This week's extra story is a bizarre source for a fast radio burst that was discovered last year. The call is coming from within the solar system. And I'll put a link in the show notes. I've got an interesting comment that I want to respond to about sort of hoping for catastrophic space events. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew M. Gross, Barry Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bieluk, Cy Nielsen, David Gilton, David Matz, Dustin Cable, Evan Pro, Greg Feely, Hudson Ward, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Marcel Smith, Michael Purcell, Modzo, Paul Robach, Ren Kaidu, Robeck, Sean Sargent, Stephen Fowler Munley, Vlad Shiplin, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So we got a comment on Space Bites Plus, which is the Patreon version of this exact same video. And Norm W asks, is it wrong to hope that the asteroid hits the moon? I think that's funny because, you know, there are these events that are potentially catastrophic, and yet you kind of want to watch them happen. You know, you think about how, if asteroid YR4 does hit the moon in 2032, then it's going to release a bunch of shrapnel, and some of that is going to reach Earth. We're going to get the mother of all meteor showers. It won't be dangerous to us, but it could be dangerous to our satellite. So on the upside, you get this really amazing meteor storm for, a couple of days, maybe a couple of months, but you also potentially lose a bunch of our satellites. Worth it? I don't know. And then you think about, say, when Betelgeuse goes off, right? Like, we're going to have this star that is going to detonate in the sky, and we will be able to watch this new star for a couple of weeks during the daytime and still see it over the course of several months. It's going to be epic. And yet, you know, a star died. Were there planets around that star? There are ethical quandaries, things you have to be concerned about. And so a lot of the events that we see in astronomy are often the most catastrophic events that are happening. These are things that are stars crashing into each other, black holes consuming planets, stars. You know, if there's nobody out there, if there's nothing out there, then it's all fine. It's just rocks eating other rocks. It's balls of plasma eating rocks. It is black holes eating rocks. But if there's people on them, if there's civilizations out there, if these are what we're seeing as a cool light show is a catastrophic event, then it kind of changes the sort of the calculus of this. And then I also think a lot about how things that are beyond our life, you think about the end of the Earth. You think about how in a billion years, the sun is going to heat up to the point that the Earth can no longer hold its water, that the sun will turn into a red giant billions of years after that, that the heat death of the universe, a Google years from now, will get to the point that no useful work can ever be done and all life in the universe must cease. And you sort of feel a little nervous, like that's just around the corner, but it's not. And yet, I don't know, it's funny how we can personalize this and think about this. So, it's interesting to me to sort of think about how we have this connection and this sort of emotional reaction to the things that are happening out there in the universe. And I think it's a good thing. I think it connects us and it grounds us and it fills us with wonder. And we think about the future and the possibilities and think about things that are larger than ourselves. And I think that's always really important. All right, we'll see you next week.